AI has a heat problem. Every time an artificial intelligence system answers a question, generates an image, or processes enormous amounts of data, thousands of processors may be performing calculations inside buildings most people will never see. Electricity enters those machines, computation happens, and almost all of that electrical energy eventually ends up in a much less futuristic form, heat. For a laptop sitting on your desk, removing that heat is relatively simple. A small fan pushes warm air away from the processor and into the room. But take that same basic problem and multiply it across thousands, sometimes tens of thousands, of high-performance processors operating together, packed into dense racks inside enormous data halls, and cooling stops being a small engineering detail. It becomes infrastructure. And this is where artificial intelligence begins to collide with another physical resource that seems completely disconnected from software. Water. At first, that sounds strange. Computers don't drink water. Artificial intelligence doesn't require water to perform mathematics. A processor can execute billions of calculations without a single drop of water flowing through the silicon itself. So why are data centers increasingly appearing in discussions about water? Because computation produces heat, and that heat has to go somewhere. Inside a modern data center, processors transfer heat into the system surrounding them. Depending on the design of the facility, heat may move into air, into liquid circulating close to the computing hardware, or through several different cooling loops before eventually reaching equipment designed to reject that heat outside the building. The basic physics are surprisingly simple. Electricity enters. Computers perform work. Heat comes out. And if that heat cannot be removed continuously, the computers cannot continue operating normally. This means that a data center isn't simply a warehouse filled with servers. Behind the computing equipment sits another industrial system: pumps, pipes, fans, heat exchangers, chillers, cooling towers, control systems, and increasingly sophisticated forms of liquid cooling designed to handle processors that are becoming more powerful and more densely packed together. From the outside, artificial intelligence looks digital. From inside the building, it can look remarkably industrial. And water enters the story because it is extremely useful for managing heat. Some cooling systems use evaporation to reject heat into the atmosphere. Others circulate water through cooling equipment. Some facilities use closed loops in which liquid is repeatedly recirculated, while others can combine different technologies depending on weather conditions, operating loads, local water availability, and the design of the data center itself. That distinction matters because saying that a data center uses water can hide several very different things. Water circulating through a closed cooling loop is not necessarily being continuously consumed. Water withdrawn from a source is not always the same as water permanently removed from that local system. And a facility using evaporative cooling behaves differently from one relying heavily on air-cooled or mechanical systems. There isn't one universal data center. And there isn't one universal number describing how much water artificial intelligence uses. That is one of the reasons simple claims about the water footprint of a single AI question can be misleading. The answer depends on what hardware performs the computation, how efficiently that hardware is being used, where the data center is located, what the weather is like, how the facility is cooled, and even how the electricity supplying the computers was generated. The same computational workload can therefore have very different water consequences depending on where and how it runs. And once you understand that, the real AI water problem begins to look very different. The issue isn't simply that AI needs water. The issue is that enormous amounts of computing are being concentrated into specific physical locations, and every one of those locations exists inside a real environment with its own climate, electrical system, water infrastructure, industries, farms, and cities. Imagine two identical AI data centers. The servers are the same. The processors are the same. The computing workload is the same. But one facility is located in a cool region with abundant water resources and access to reclaimed water, while the other operates in a hot, water-stressed region where the same resource is already supporting homes, agriculture, and industry. Technically, both facilities may be doing exactly the same thing. Locally, their impact can be completely different. This is similar to the electricity problem we saw before. Globally, the world produces enormous amounts of electricity, yet an AI data center can still struggle to find another 100 megawatts at one particular location because power has to reach that facility through specific transmission lines, substations, and transformers. Water has its own version of the same geography. The global total doesn't tell you whether another large industrial user can be supported inside one particular watershed. Water that exists somewhere else is not automatically useful here. And that makes location increasingly important. For decades, data center location decisions were heavily influenced by things like electricity prices, network connectivity, taxes, land availability, and proximity to customers. Those factors still matter. But as facilities become larger and computing density rises, the surrounding physical environment matters more. How hot does the region become during summer? How humid is it? What cooling technologies make sense there? Is reclaimed water available? How stressed is the local water system? How carbon intensive is the electricity supply? And perhaps most importantly, what happens when several enormous facilities arrive in the same region? Because scale changes the problem. One highly efficient data center may be manageable. Then another arrives. Then another. Then an entire cluster forms because the region already has fiber connections, available land, favorable regulations, and access to electricity. Suddenly, something that looked insignificant on a global chart can become important locally. This is one of the recurring patterns underneath modern infrastructure. The world doesn't necessarily run out of a resource. Demand simply becomes concentrated faster than local systems can adapt. But there is another complication. Suppose a data center operator wants to reduce its direct water consumption. One apparent solution is to rely less on evaporative cooling and more heavily on mechanical or air-based cooling systems. That can reduce water use at the facility. But cooling equipment requires energy. And depending on the system and local conditions, reducing water consumption can increase electricity consumption. Now the problem begins looping back on itself. AI needs electricity. Electricity becomes heat. Heat requires cooling. Cooling can require water. Reduce the water requirement, and some cooling approaches may require more electricity. And as we saw before, electricity itself may already be constrained by the grid. This is why infrastructure problems rarely have one perfect solution. They have trade-offs. Saving one resource can place additional pressure on another. The best design for a data center in Sweden may not be the best design for a facility in Arizona. A cooling technology that performs extremely well during a cold winter may behave very differently during an extreme summer heat wave. A facility with access to reclaimed wastewater may have options that another facility relying on potable water simply doesn't. So the engineering question isn't merely, how do we use less water? It is closer to, how do we provide enormous amounts of computing while balancing water, electricity, reliability, cost, climate, and local infrastructure at the same time? And there is still another layer hidden underneath all of this. So far, we have been talking mostly about water used at the data center itself. But a data center can have another water footprint far beyond its property line. To understand why, follow the electricity backwards again. The servers draw electricity from the grid. That electricity may come from solar farms, wind turbines, hydroelectric facilities, nuclear plants, natural gas plants, or a combination of many different sources. Some forms of electricity generation also use water. Thermal power plants, for example, may require cooling systems of their own. Hydroelectric generation obviously interacts with enormous water systems in a completely different way. Even when a data center dramatically reduces the water consumed directly on its own site, the electricity it purchases can therefore carry an indirect water footprint somewhere else. That creates two separate paths. The first is easy to see. Data center. Cooling. Water. The second is less obvious. Data center. Electricity. Power generation. Water. And depending on the facility, the climate, the cooling technology, and the electricity mix, the relative importance of those two paths can change. This is why asking, how much water does AI use, sounds like a simple question but doesn't have a simple universal answer. You first have to ask where the computation happened. Then how the facility was cooled. Then where its electricity came from. Then what kind of water was being used. And then whether you're measuring water withdrawn, water consumed, or the broader water footprint associated with the entire system. Once again, software turns out to have geography. But none of this means the expansion of artificial intelligence inevitably produces an unsolvable water crisis. The infrastructure is changing. Companies are developing cooling systems designed to reduce or eliminate the use of potable water for cooling. Reclaimed water can sometimes replace drinking quality water. Closed-loop systems can repeatedly circulate cooling fluid. Direct-to-chip liquid cooling can move heat away from increasingly dense processors more efficiently. Better thermal management can reduce the amount of energy needed to keep equipment within safe operating temperatures. And even the heat itself may eventually become useful. A data center is essentially taking high-quality electrical energy, using it for computation, and then producing large amounts of lower temperature heat. Normally, the objective is simply to get that heat out of the building. But in some locations, waste heat can potentially be captured and used elsewhere. Buildings need heating. Industrial processes need heat. District heating networks already move thermal energy through parts of some cities. If the geography, temperature, infrastructure, and economics align, a data center can become not only a consumer of energy but also a potential source of usable heat. That won't work everywhere. And it won't eliminate the cooling problem. But it illustrates something important about infrastructure. What looks like waste in one system can sometimes become an input to another. The bigger transformation may therefore not come from one revolutionary cooling technology. It may come from designing computing facilities around a physical environment rather than treating the environment as an unlimited background resource. Place facilities where the grid can support them. Match cooling systems to local climates. Use reclaimed water where it makes sense. Improve processor efficiency. Reuse heat where practical. And perhaps most importantly, recognize that the best place to build the next AI data center may not simply be wherever land and electricity appear cheapest today. Because artificial intelligence is no longer expanding only inside computers. It is expanding into landscapes, into electrical grids, into water systems, into industrial supply chains, and into communities that already depend on those same physical resources. Now return to the screen in front of you. You type a prompt. A processor somewhere performs the computation. Electricity enters the machine. Heat leaves it. That heat travels through cooling equipment, pipes, pumps, heat exchangers, and perhaps water systems before eventually reaching the outside environment. The entire process may happen thousands of kilometers away, completely invisible to the person using the AI. But invisible does not mean immaterial. The strange thing about artificial intelligence is that the more powerful the digital world becomes, the more physical infrastructure appears underneath it. First electricity, then heat, then cooling, then water. And each layer reveals another system that has to expand alongside the computing itself. But there is one resource underneath almost all of them that we haven't talked about yet. Data centers need somewhere to exist. Power plants need somewhere to exist. Substations, transmission corridors, cooling equipment, backup systems, and enormous computing campuses all occupy physical space. And as AI infrastructure becomes larger, access to the right piece of land close enough to power, networks, water, workers, and customers can become a strategic resource of its own. AI may seem almost infinitely scalable in software. The earth beneath it is not,